on Monday, I will prove for you the halting problem, as well as teach you about diagonalization and prove that there are different sizes of infinities. This is typically a mathematical high point of the class. It's not actually that difficult to do, but it's difficult conceptually because the concepts are so mind-bending. So please come. Of course, it will be recorded as well. We will have a bunch of assignments on the halting problem and proving things are computable and uncomputable in the future. Okay, so that's kind of what I wanted to say about where we are in the class. So there's a handout today on MapReduce. So now you know a lot about map and a lot about reduce, although we still have more to learn. So I want to define MapReduce as a parallel implementation of the same contract you already know from map and reduce. So the idea of this is it's a contract to parallelize. So it's a little different from the contracts you've seen before. So the idea is that if you write your code functionally and use map and reduce essentially as much as possible, then there's an automatic thing like a compiler that will automatically take your code and make it run on not thousands, not tens of thousands, but millions and tens of millions of processors without you having to write any overhead. So same semantics, but instead of being implemented on one machine or 2 or 3 nodes in your machine, implemented on not a billion processors, but up to 100 million. And that's a pretty cool thing. So this is not a systems class. This is more like an advertisement for future classes you might take in systems and computer science. But I'd like you to see this, and it's also a great exercise in learning to know more about functional programming in MapReduce. And as I said, this is widely used. Now, this is something that is actually a little bit easier to show using sharing screens and PowerPoint and so forth, so I'm going to do that. So let me share my screen here. Go, share screen. Good. Let me know, can you see that shared PowerPoint?
Yep.
Okay, good. All right. So I have added to these slides, but these are slides from friends of mine at Google, which invented MapReduce in some sense. And these, some of them migrated to the University of Washington. And one of the things I want to show you is that this functional programming in general, and this weird map and reduce thing, it's not just a strange Duke thing in a strange math class. This was actually not only the concepts, but the slides. Many of these slides are actually from Google. This caused a revolution in parallel distributed programming. And I think it's useful for you to see this. Now, there's a lot of advanced things I'll touch on here. You're not responsible for any of it. You're responsible for the scheme code that I'm talking about in the concepts. But I'm not going to ask you to write parallel programs. That will be for a class like 316 or 517 if you take it. But this is used widely in industry. All right. So this is most of these slides are actually from Google, but I'll talk over them. So the idea, work was originated in 2004, but it's still used today. So we want to use thousands of computers. So you might notice that a lot of these computer science classes were using one computer or two. There are very few that use lots of these things. And the reason is it's real hassle to manage these. So MapReduce, which is a framework, again, based on the functions map and reduce that you know and love, that provides for automatic distribution and parallelization of your programs and other things like fault tolerance and so forth that you need to have in an actual working system. So kind of cool. Now, again, the programming models from Scheme. Again, these slides are from Google, right? And turns out you can phrase lots of problems this way. It's super easy to distribute across nodes, and it's also quite robust in a sense that I'll try to get into about what happens when there are failures in such a big system. So this is my code, or our code for the class. I want to remind you what we have here. We went through map and accumulate. You're experts on this. You even had a midterm on this as well as some assignments. We know what these things do. We've even worked in problem 5B of writing, essentially writing map is a special case of accumulate. So we know what this is now. The thing is that there are many names for these things in the computer science and programming language community. And it's Google people are from a dialect that call it reduce instead of accumulate, same thing. So we use reduce here. Now you see what map and reduce are. But how does this relate to parallelism? So here's the idea, the basic idea. You should know this. If you only get this, that's fine in this class. So we're going to write a program in Scheme. And one of the reasons I want you to write in this style is that if you write these big, complicated things using lots of helper functions, and letrec is basically looks like Java translated into Scheme or Python translated to Scheme, there's no way you could ever parallelize that without hiring 5 or 6 master's level technicians or getting a PhD in computer science. It just isn't going to happen. It's never going to run fast. But if you basically take every opportunity you can and use map and reduce, then you can run the program on small instances. Regular versions of map and reduce will work just fine. But when you run this special if you were compiler, it'll automatically replace the functions map and reduce with operators that are parallel implementations on a huge cluster. So the system handles all the details. You just write the functional program. So in some sense, they become parallel operators. So the way I like to think about it, not to steal a leaf from the book of Joe Pesci, it means parallelize this. Every time you say map, every time you say reduce, you're telling the compiler, take this and parallelize it. And especially if you use them in close proximity, it knows how to do that. And I'll give you some hints about that. So that's pretty cool. So all we have to do is learn functional programming. Hey, you already know that. Map and reduce. Hey, you already know that. You're ready to write big parallel programs. Okay. So back to the slides that are actually from Google. So again, they want to remind people what map is, right? So you already know this, but I want you to actually see the slides. And by the way, these slides are on the web too. So remember what map does. Here's how they describe it. Map square over this. You have a unary operator. We can map things over. Reduce works in this fashion. We take a binary operator, a base case, and we take a list. And we basically combine this in various ways, unfolding it. This is also called fold right. And we get an answer like this. And of course, you can combine these together in various ways. We can apply reduce after map, right? This adds up all the squared things after we've subtracted 2 lists. So this is an example, a paradigm, not one that's going to be very alien to you, about what happens when we cascade the maps and reduces. So this would be a good example of a nice functional program that we would like to use, right? It has a map, and a reduce. This is the kind of thing that the MapReduce compiler could automatically parallelize for you. And if this seems a little bit alien, maybe you're just getting into computer science, or maybe you're a mathematician kind of interested in computational issues, it's worth sitting down with a big cluster, and we have these at Duke, and taking what you know about CS and math and saying, well, how can I write a program that somehow works and coordinates between thousands of machines? It's entirely non-trivial, and MapReduce gives that for you. It's kind of a neat thing. All right. So
there's a question, Professor Donald. What does it mean to parallelize?
Okay, so suppose you have a program that runs on one machine, like Racket. Now, I know that inside you might have 7 cores and so forth, that's taking care of you, but you have some program and it's slow, like you're doing RSA or something. So runs on one, say, laptop. Now, you know that down the hall, your professor has a cluster, or Duke has a cluster, or bioinformatics has a cluster, or someone has a cluster, or Amazon Web Services has a cluster, right? It has a cluster with 1,000 processors or 10,000 processors. What you'd like to do is press a button and have your program run on thousands of machines and processes rather than just your laptop, and hopefully get a commensurate speed up. Does that make sense? Hello?
Yeah, the answer in the chat is yes, that makes sense.
Good. Yeah, I can't see the chat because of my setup, but I'm always happy to. I mean, I sometimes can see it, right? It just basically flies by, but feel free to just interrupt. Great, sounds good. So parallelize is to make parallel, and parallel means running on many machines at once. And again, there are later courses on this, but I'm giving you kind of a peek at what some of those might look like, although they don't all use this mechanism. Okay, so let me give you an actual example here, but we'll do it in Scheme. So most of the things Google's interested in are search, documents, indexing, that kind of thing. So I wanted to give you a little mini example. And the mini example you can imagine a document being a paper. So this is abstract of one of my papers, which happens to be on HIV. It's got lots of things in here. Suppose we wanted to count up how often words occur. This is actually a pretty important task in indexes. So we apply some function called word count to the document, right? And we want to write this using map and reduce. And obviously, I'm sure you could write this program using various iterative things. You might even write it recursively. Can we write this using map and reduce? So the idea is we would count up how much each word was used in some sense. That would be the task here. So we'll work this as a kind of example today and look at how to think about this problem. So document is a list containing these atoms, word count, how many times does vaccine or HIV or membrane or protein occur in a document. All right. So again, if you read this paper, they use a kind of different terminology, mostly because they don't have scheme semantics. So they have to kind of, get around that somehow. So, the last form in a expression is what it returns. You have a function, it returns the last thing always, right? So they use the term emit. You have to explicitly return something, right? And there's also some wishful thinking in here. You have keys that you're searching over. They use the term unique key. And that tells you that you somehow have to actually make these keys unique, right? You have to find a way to do that. So it's kind of, again, little verbal jujitsu that they're doing. I like this paper very much, but I'm trying to translate it into our very mathematically grounded work. So basically, if you are doing this to actually get out of the unique, make keys that you're searching over, like keys being words, for example, unique, you have to do things like remove duplicates and filter and so forth, and maybe hash. And that's kind of the way they think about this. So again, they're explicitly returning things rather than just letting the list form do it. So here's how they think about it, right? They have an infix notation here for this. So what they do is they have this expression that you might call map a key over a value. So you run this sort of process over some pairs of values in some sense. And that's kind of how they, view this process. Now, and again, it returns, so you basically have some function and you map it over these key value pairs in some sense. So you have these keys and values have to describe what they mean. But in this case, the key might be an actual word like HIV or membrane or protein, and value might be how many times you're counting it up. That's one way of thinking about this. Now, reduce, again, is exactly like reduce, and they think of it this way. So you run reduce like this, and you kind of collect the outputs together. And here an example would be a little bit easier, I think. So basically, it's very obscure, actually, when you read these papers. So let me give you maybe you haven't read a lot of computer science papers, or why would you? But what I do when I read computer science papers is I say, oh, they're implementing something. Well, I don't think I understand that. Let me try to implement it myself, right, based on their description. And if I can do that, then I understand it. So remember, as Richard Feynman says, what I cannot create, I do not understand. So when I got this weird description of map, I was like, well, I can write that. So here's your example in Lisp, right? So we have this is how we're going to do it. So we're going to map this thing over a document. Remember, a document is going to be this thing here, like just the text, basically. So what I'm going to do here is I'm going to map this thing like this. So look at this little function here. What it's going to do is it's just going to make a list of all the words followed by one, right? And then reduce is going to add these things up. So the map step is really very straightforward, right? So basically, instead of a list of documents like I will make a vaccine if I am lucky, instead it will be I one, will one, make one, a one, vaccine one, and so forth. And I'll show you the code in a minute. So reduce has to then add these up when the words are of the same type and then return the final output. So map was easy. What does reduce look like? Well, we have to do a little work to see what that is like. So again, I want to sort of imply that what I'm doing here is a paradigm, right? When you read these complicated papers that are using English, so you can't always decide exactly what's going on, although you can see what's claimed, what you should do if you want to be a computer scientist is write the code yourself. Same for math, you do the proof yourself. So for biologists and chemists, they report the experiment and the results. And replicating the work and making sure it's true is running the experiment yourself and reproducing the results. For a mathematician, it's checking the proof. For a computer scientist, it's constructing the code that does what the authors say. And this is how you know what the paper really did. And that's what I did with this paper for y'all. Okay, so here's what map does. I have this document. I map this little function here over it. I get this weird thing that looks like this, where I have all the words followed by one. And then reduce will somehow process this. And when the words match, like the word vaccine, I'll add those up and return those numbers. So let's look at the code for that. So the first thing I have to be able to do here is, suppose I do have two words that are the same. Suppose I have a word like roadblock and it appears somewhere else. I have to be able to add an item that has type roadblock 1 and another thing that has type roadblock 1 together. So I have to be able to add word pairs. So I have to write this little helper function here that basically just adds the counts. And of course, the words have to be equal. And now I can count words in a particular document. So notice what I'm trying to do. I'm trying to do two things, use the functional style, good clean code, and I'm trying to, whenever I can think of it, I want to think about how to use reduce and map, because I know that will make the program faster when it's parallelized. Again, imagine you have a server at Google with a farm that's consuming like 5 gigawatts an hour, and you have a 500,000 processors that are all running over all documents in the world in order to index them constantly as we speak. So big task. So again, this will add two word pairs, a word pair being a thing like major or roadblock followed by its count in the document, and it just adds up the second one. So here's how you count an actual word. Well, what you first would do is the thing we had before. So in red, that's going to be replaced by this big list like this with all the counts, which is fine. And then what I have to do is I want to count a particular word. So this counts a particular word in the document, say entry. So I have to filter out of this big list all the things where that match that word. And then I add them up using reduce. And my base case is just the word with 0. And then at the end, I'm going to add these up and have a count. So how does something like this actually work? If I look at my document count vaccine, I find 2, HIV2. Oddly enough, the word the is 10. And if you're interested in natural language and document understanding, this is actually an issue because you might think that the is the most important word in the document, probably is the least important word. But now we can count words in the document using just this little bit of code that uses to some extent map and reduce. And of course, we can nest another map around this. So here what we've done is we've basically taken this procedure here, and what we've done here is we basically mapped that over 3 words. So now we can simultaneously count, not simultaneously, but in sequence count vaccine, HIV, and the, and get counts for all these words. So now we have a start on how we're going to count words in a document. And again, I've just told you of this strange goal that I have, which is to use map and reduce as much as possible. And of course, everything has to be functional. As soon as you have any side effects, then it's extremely difficult to parallelize these. When I was a grad student and young professor, basically, every time there was a new kind of side effect, it took 2 or 3 PhD students to figure out how to even, in a kind of half-hearted way, parallelize that and get 2-fold speedups. Whereas with techniques like this, we can get million and billion-fold speedups without even having to think about it. So it's very nice to use the functional style because you can write programs that run on lots of processors at once, i.e. parallel programs. All right, let's go a little further. Now, the exercise here is a programming exercise. We have reduces and maps here, but what about filter? So this is a lot like your problem 5b in some ways. Could we actually write filter using map and reduce? And if we could, that would be a win because instead of being a serial operation, i.e. one at a time, it could in principle be parallel and recognized by the compiler. So let's see if we can write filter in the same fashion. So, well, here's one way to write filter. So I've written filter using a call to reduce. So I pass in a predicate and a list, and I basically cons up all of the things here where the predicate is true. Otherwise, I just don't add it on. So here's an example. If I use my version of filter above, with the predicate odd, I can just return the odd numbers. So interesting exercise, right? It may seem kind of abstract, but it's motivated here by someone circling this, your boss saying, hey, Bruce, you did a nice job, but you can't parallelize this. It's going to be a bottleneck. You have to make something to be recognized by the MapReduce compiler. It has to have maps and reduces in there. What can you do? You go back the next day, you say, look, I've done it, boss. I have written filter by a call to reduce that works like this. Again, very similar to problem 5b. And again, the answer that you might have returned for 5b might have looked like this, although you were writing map instead. But this is considered good idiom and good style and also easy to parallelize. So now we've written filter. Let's go a little further. What about removing duplicates? I sort of said we had to remove duplicates in order to do stuff. Well, we can remove duplicates also using reduce, right? So I won't go into this. I'll let you read about it. The notes are there, but I can remove all duplicates from a list. I call it remdupe. Remove duplicates from a list like this, and I can write that using reduce, which also will be to some extent parallelizable. So now I have some basic tools that I've just rewritten in the style using map and reduce. And remember, I'm asking you to believe in a contract here, right? We already have the idea that when you state a claim to a theorem, it does have to be proved, but once it's proved, you can rely on the theorem to be true in the context of the antecedent. And similarly with a program, you've gotten pretty comfortable with me sketching out some code and then saying, okay, now we have to actually implement these 5 functions that are called in the top level function, right? So this is just good software engineering and good mathematics. We have the same exact paradigm here. I promised you that if you use map and reduce, you can parallelize things and make them faster, but you have to actually write the code for that. So the exercise in parallel programming is one in which we try to use functional programming and to use map and reduce all the time. But basically, these are not very deep things here, these filters and remove duplicates. They're basically wrappers around this. So you can sort of think of it as just some amount of code that's a wrapper around calls to reduce. And from this viewpoint, it's also very interesting because you can see that remove duplicates and filter are essentially forms of reduce, which is kind of a very powerful, not universal, but very powerful computing mechanism. Okay, now let's rewrite our way of counting a word. Remember, we had a call to reduce. Inside that, we had a filter, and then we had a map inside there. We could just replace these with the wrappers like this, and we get something that looks like this. So, you know, and again, I'm not so worried this says filter here because the filter is actually a call to reduce. So that actually is fine. So I have a nice nesting here. I've reduced here. I have a map here. So I have a nice alternation, so to speak, of reduces and maps, which is what I want. So now, as always, we're going to abstract. I don't want to just count one word. I want to count all the words in the document and report them back. So how do I do that? Well, we're going to use map, of course, to map this across all words in the document, just as I did before for the words vaccine, HIV, and the. So that'll be another map on the outside. So here's the example I did before. In the same way that I want to just map over these 3 things, instead, I want to map over the entire document and have this be sort of a modular thing. So another map around the outside. And of course, as usual, I have to sort of customize the function. And let me mention that what we're essentially doing is a form of currying here. And in fact, some of you geniuses actually solved problem 5b by explicitly using the function curry. So gold star points for doing that, understanding how high order procedures can be super helpful here. But here I'll manually curry it myself. All right, going on. So I want to count all the words in a document. So notice I'm going from count word here to count everything in the document. So what I want to do is basically, in the same way that I mapped count word over a document containing 3 words, now I want to have a general procedure that will do this over the entire document like this. So I map now my curried count word like this over the document once I've removed duplicates in the document. So in the document, I'm counting all the words, but I don't want to make an entry in here where they're duplicates. The index only has things once. So think of it this way. If you look at an algorithms textbook, probably tree is mentioned 572 times in there. But you don't, in the index, have 572 entries to tree that are identical, right? You have one entry. So this is making the index, which is a non-redundant set of important words, then we're mapping count word over that. Now this is great, you know, as we have it, but we want to do, we want to see how this works. We also want to expand it a little bit. So how does this actually work here? Like we have working code. When we do this, we're going to get the following count. So when I actually run this code, and I'll run it for you in a minute, we have a document like this. We have the word count, which is the thing, and we get a count. How many times is every word used? I've also used the sort function to have the most frequent ones at the beginning, which is a post process. So the most important word in my abstract is the, but we also have important words like membrane and region and HIV and so forth that are used in this little example here. And we'll look at this code in just a second, although you basically have the idea, I think, at this point. Now, it's really nice to name count word, right? That's an extremely good use of names. It absolutely deserves its own function. But let's see the actual parallel pipeline by unwrapping all the steps in the functional programming and see how often we use map and reduce here, right? And remember that filter and remdupe are just wrappers for reduce, right? They're just basically a call to reduce with a little bit of wrapping around it. So I'm going to unwrap this now. I'm going to replace count word by the full pipeline just so you can see it. It now looks like this. So basically, our count word thing is a reduce. Remember, filter is basically, you know, of course, going to be this really nice thing. So we started with count word here, right? So count word is reduce, filter, and map. Now we want to do this for everything in the document, and we're going to get this. This is our final word count. So look what we have here. We have, going from the outside in, we have a call to map. We have a call to reduce. We have a call to filter, which is a wrapper for reduce. We have a call to map here, and we have a call to reduce to make the index like this. So now we can count all the words in the document. Again, this is better, probably easier to understand code because we've named what we're doing, but this will show the parallel pipeline, namely not alternating, but a series of calls to map and reduce. We've actually used map and reduce as pretty much as possible. You know, it'd be interesting to have a theorem that said you couldn't use map and reduce anymore without actually slowing things down, at least in a serial case. I'll leave that for you to think about. So now we have a method to do this. And all we needed for this were the things I've taught you, right? So now we can do parallel programming. In order to do this, we needed the lambda calculus, because otherwise what do our programs mean? We need scheme because we need an actual programming language that implements that. Substitution model gives meaning to our expressions. Functional programming, because we have to do this without side effects, otherwise the parallel program cannot be parallelized. In other words, the putative parallel program will actually be slower. We need higher order functions because that's how we will implement map and reduce. And of course, you could prove these things are correct by induction. So it's the exercises to prove they're correct by induction on a serial program, and then let the compiler do this for you automatically. Now, I want to go back to Google in a sec, but let me actually show you that this is working code. I don't think you doubt me, but it's really not that complicated. Here's my bracket window here with my code for this, which is basically what you can see. It's probably a little hard to see because of the font, but you can see I have reduce and filter and map here. I have add word count pairs. I have count word down here. And over here, I have word count for the document. And I have my document at the end. And then I have some utility functions. I sort them at the end. And if we actually run this, it should do what I said. So you can look at this code, and if you like, and look at the slides into more detail. But the main thing is there's actually operational code that does this, of course, running on a single computer, namely my fairly old desktop here. Okay. And a little easier to see like this because I made it larger. Okay. So again, we now have all the tools to write programs like these and understand them. And if my goal was to get you as quickly as possible to writing MapReduce parallel programs, you would need all of these steps. In fact, my goal was to get you to next Monday's lecture, which is on Alan Turing's halting problem, which is the single deepest result in computer science, even though it's nearly a century old. But it turns out that as a side effect, no pun intended, we also get parallel programming for free via Google's MapReduce. Okay, let's look at a little more detail of what the Google paper says. So again, let's go back to where we were before. This is how Google describes map, how they describe reduce. We know that we can write this very cleanly in scheme like this. We know exactly what this first step means. So in other words, I would view this thing here as just words, right? It's pretty clear words, but there could be ambiguity. When I've written it as a language, in an actual language, like scheme, I actually know what's going on. Same for reduce. Remember, we now have this program that can count words for us. Now, they have an example, and you can compare the syntax between the scheme syntax and what they use, which is a combination of sort of C++ or Python or something. So they view this as follows. So for them, all documents are actually URLs, right? They're interested in stuff on the web. right? So the unique key is the URL. Contents is what's actually in the page. When they do a map, they're basically counting these things. The input is the URL and the contents, and they want to actually emit pairs, just like I had with the word, for each word, and the value 1. And reduce is going to sum up all the ones in the list and emit word and sum. So I'm just showing you two different views of the same thing. We've already written our scheme code. We know exactly what it does. This is how Google describes it. It's the same thing, but using kind of an infix way of thinking about it. All right, so here's their example. Again, it's a little simpler than my example. Our text here is see Bob throw, see Spot run. We do our exact same thing here, which is our map and reduce here like this. And when we do this, we first get these counts. We get these pairs, the word and 1. That's the map step. And the reduce step then adds these up and sees that we use the word see twice. That's the example. The red arrow is a map. The purple arrow is a reduce. Okay. And here's their actual code. You can see it's infix notation. So map, which corresponds to our map in the upper right-hand corner, looks like this. That's how they do a map. Reduce is implemented like this. That is the usual kind of C-like notation there for incrementing something. So we have our map and reduce in scheme. They have their map and reduce in this language here, which is an infix, more traditional language. They do the same thing. All right. Now, let's look at a couple of other applications you could do. These are mostly in the paper, but I just want to mention them here. I'll go in far less detail. So grep, as many of you know, is a Unix function. You know, can you search through a set of files for a string? Can you implement this with map and reduce? So the thing is, grep is pretty slow. If I search through all my files, which are many terabytes from many universities and companies, and I'm searching for a particular letter of recommendation for a student who took my class in 1989, and can I still write something about them? It could take a long time to find that. But if it was parallel, maybe all those processors could divide it up and search in some really nice way. So again, the input, the keys are URL plus some offset to where the line is. The actual text will be a single line. And what the map is going to do is basically just going to emit the line and a 1 if the contents match. And reduce doesn't do anything. It just basically is the null operation, just emits the line here. So the point is, the actual things you're doing with map and reduce in the Google MapReduce paradigm, by the way, also used by Amazon, Facebook, Yahoo, Amazon, mentioned twice, ITA software, same paradigm, but it can be a very simple operation, but because it's being put into this framework, it can run very quickly. So this is how MapReduce can be used to implement grep. Here's an interesting example, reverse web link graph. So can I find all pages that link to a certain page? So again, you can coerce this into the MapReduce framework. What map does is for each URL that links to a target, you output a pair, which is the target and the source, the head and the tail of the arrows. And reduce basically concatenates this list of all the source URLs and inputs up to something like this, a target, and then some accumulation of all the source pairs. This would be an append or a bunch of conses in our paradigm. So you're accumulating this with consing up a list of these different sources here. So you can do reverse web link graph, which is actually pretty useful using MapReduce. So all this kind of web stuff, this powers up a lot of what Google does, which is obviously an industry powerhouse. An inverted index is another example. So this is a data structure that's of some interest here. Basically, it's a mapping from content, like words or number, to locations where it's used, basically. So this is a way to make full text searches super fast, right? It's a kind of pre-processing that you do for a document, so you can do these full text searches really, really quickly. So it's used a lot in document retrieval and search engines. Machine learning uses this as a subroutine because you want to index these documents really quickly. And that can be done also very quickly using map and reduce. And I am going to leave that as an exercise for you to think about, but we're happy to give you hints on it, and also it's in the handout lecture notes for today. So I've given you one example in detail, which is word count. Two, I've claimed there's a solution, And I have a fourth one here that you can think about and try to implement. So it's more than lists and scheme, it's URLs and file systems and things on the web.
So Bruce, we have a question. It's
Absolutely.
asking how many, can every program be kind of coerced into this MapReduce framework?
The answer is no. The answer is no, you cannot. So it's a challenge, right? If you have something and you try to write it this way, you might be able to get something that's parallel. However, if it can't be coerced into this framework, it might be very difficult to parallelize. So one of the deepest results, well, in parallel programming is that there's some functions that are inherently difficult to parallelize. Let me give you an example. Think back to high school or perhaps to first year calculus. Do you remember what matrices are, and do you remember what the determinant of a matrix is? Is that familiar to anyone in the class?
Yes.
Okay. And we won't use determinants very much. So one of the things about a determinant is it has alternating signs. Like even for a 3x3 matrix, some of the entries are positive and some of the entries are negative. So you typically are multiplying things together in the matrix. Determinant is always a scalar value, right? But it's basically an alternating sum, more or less, of products of the entries in the matrix to give you that sum. So this is called a determinant. And it's relatively easy to parallelize a determinant. Why would you want to do that? Well, in control theory and in machine learning and some other applications, sometimes your matrix might be 1 billion by 1 billion or 1 million by 1 million. And doing the traditional algorithm you could do in high school or freshman calculus is way too slow. It'll never converge and take up way too much space. So fortunately, there are very fast algorithms for both estimating, bounding, and computing the determinant beyond this class, but not much beyond. Let me introduce another weird thing called the permanent. The permanent is just like the determinant, but all the signs are positive. Whereas the determinant can be relatively easily parallelized, the permanent cannot. So determinant fast, permanent not. This is one of the deepest conundrums in theoretical computer science, trying to figure out why that is. What is the obstruction to parallelizing it? So the question, I didn't see who asked that, but feel free to let me know afterwards so I can praise you. The question is extremely deep. So we're going to confront this now in terms of programming exercise. If you want a parallel program, try to write it functionally. If you can, you'll get parallel speed up. Then try to write it using map and reduce, or do both at once. If you can do that, you'll get an unbelievable speed up, and also it will be extremely easy. If you can't do those things, then you're either we don't know, or your problem is difficult to parallelize. And we can get into that a little more later. So right now, for you all, writing a parallel program is as easy as writing a scheme program. But in a conventional computer science class, you can go through 5 or 6 years of writing serial programs and taking lots of algorithms and theory classes. And then when it comes time to write a parallel program, you have no idea how to do it because it's a completely different set of skills. The nice thing about our paradigm is that as soon as you can write functional programs, and as soon as you can use map and reduce, you can immediately write parallel programs. You don't need another 6 years of training. And that is a huge, huge advantage. So whether or not you can write those programs is not harder than writing a program to begin with in this class. But we don't know that we can write all programs. And I'll talk more about this a little bit on Monday. So great question involving lots of philosophical discussion. Other questions before I go on?
There's a question of why are mat and reduce so-called automatically parallelizable? What does it mean to really parallelize these two functions?
Yeah, I mean, that's a difficult question. So basically, I'm asking you to accept that there's a contract. I'm going to show you a little bit about how these things work. But from the point of view of this class, the way you should think about it is that some very clever guys figured out how to use those two operators and find a way to make them parallelize your code. So in other words, in this case, although this isn't what the class is about, think of it as a library. Like if you didn't have a stream library, you couldn't use streams, right? And you would be stuck, no infinite objects. I mean, that would be tragic for a mathematician, right? No infinite objects, oh my God. But someone gave you a stream library and I taught you how to use it. So now you have infinite objects at your fingertips. Similarly, these two guys, they figured out how to make, map, and reduce, let you parallelize things. So now you can use the library. But let me give you some insight into maybe how that works. It won't tell you the answer, but it'll give you some idea. Let me start with a little economics, if you will. So the culture at Google is pretty interesting, right? They produce these things and then make other people try to use them. So this is the growth in people using MapReduce in that first year. So basically they put it out there and gave some talks internally and externally about it, and people within Google started using it for all sorts of different things. Not just what I talked about, but lots of different applications. So sort of explosive growth in using this in the first year. This is a case study at this point because this is a classic technique, but still very interesting. And so typically you would, at those days, you'd implement them on thousands of rather small computers. Now we implement them on much bigger ones. Again, these are their slides. I just want to give you an idea of what happened. And I do want to get to the question of kind of how would this be implemented. But you see I have implementation in the title here. So we're getting close to the concept of how it would be implemented, which I will sketch. All right, so now I come to your question. Well, how do you do it? How is it distributed? What actually happens here? So basically, we have to divide up the tasks sometime. And this is how systems people talk about this. I mean, I'm sort of a systems people. My lab writes a lot of code, but really a algorithms person. You have to partition or divide up these spaces in some fashion and then run tasks in parallel. So this is the basic idea. If I have a lot of these maps to be done, divide them up into pieces. And after the maps are done, we got to consolidate the returned values and put them together with reduce. And so we have to, and then you can run the reduces in parallel. So how do you divide up these tasks? And then we have to have a failure semantics. What happens if these nodes die? And the one here is just run it again. But I'm not going to get into error detection and recovery here. Actually, my thesis was on the mathematical model, error detection and recovery. But this is a tricky subject, so just realize there has to be a semantics for what happens when things fail. You can't just throw someone out into the interpreter. All right. So here's sort of a way to think about this, is that there's some head honcho called the job tracker and a bunch of tasks, right? So these guys are going to be dividing up your task into lots of different things here. So if you say, hey, job tracker, do grep, then that has to somehow distribute this to all of these nodes and have them divide up the work. So that has to be done somehow. That's really the key question. I'm just rephrasing the, quite perspicuous comment from a student earlier who said, how do you actually do this? You have to break up the file into a bunch of chunks and assign the work to these guys. And then after the map, these task trackers have to exchange the map output and build the task for reduce in some sense. This is how it's actually done. And then after that, the reduces have to happen. The sort of head node here tells everyone to do the reduces and assigns the work. And then reduce output has to go to the file system and you can read it out. Again, I'm just giving you a sketch of the things you have to do to they had to do to implement this. For you, it's all done automatically. You just tell it how many processes you have and how many processors you have and how to access them. So here's one way to think about the problem. So a little strange, but this is how parallel programmers kind of think of things. The output is this huge, if you will, vector like this, right? And we break it into pieces, which are these lines, and these are map tasks here. So all these maps happen in parallel. And you can see why that makes sense. If I take my document, which is on a new antibody that is a potential prophylactic agent for HIV, then it's a long document. I can break it into these pieces. I can just count the words in this part of the document. This is the abstract, the introduction, the methods, the computational work, the data. Divide it up, have map work in parallel. All the maps can be done in parallel. You could count words in different sections of the document. The same way if you all were sitting in my classroom in Gross 107, which I wish you were, I could count the left side of the class and the right side of the class independently, and I can then sum them up later. So you get these intermediate values, which correspond to, the counts for each word. I have to group these together somehow. There's some operation with communication here where I basically collect things. So key 1 is here and here. I have to collect them together. Once they're grouped, I can do the reduces. So this is a tricky thing. I have to move information around. If I have key 1 here and key 1 there, and key 1 there, I have to group those all together like this, have the reduces, sum them up. So that's kind of a lot of work. How does that actually happen? So one way to think about this is we divide this up into parallel execution. Clearly, these tasks can be divided up, right? I have this first map task here, these map tasks, all the maps can run in parallel because I'm just, say, counting words or something. But then I have to exchange information. If down here, I really want to have certain values, I want to count up key value 4, I have to get that information somehow from here. So there's this step here where these processes need to exchange information and communicate. And what they have to communicate depends on the result of the maps. So I have to have this communication phase here where they kind of exchange information. So the reduces have all the places, all the data they need to actually do this summing of the word count. So remember, for the sake of illustration, our map task here is counting words on these tuples that are word, comma, count. Our reduce one is counting up the counts for words of the same type. If K4 is the word vaccine, you only want to count up tuples of the form vaccine, comma 1, not tuples of the form protein, comma 1. That would be counted somewhere else. All right. So one way to think about it, one thing parallel programmers always do, and systems people, they find these clever ways to kind of visualize how this actually works so they can see how something is going. This is not a simulation. So basically, you can imagine having a little matrix here where time goes like this, and we have all these workers, and we have a head honcho. The maps start like this. They take some amount of time. These read steps are where basically a process is reading for somewhere else. It's pulling data because it needs it. You can't reduce until you have all the data that you need. You cannot reduce until you have all the data that you need to reduce. So things look like this. You have these maps. As they're going, you can start to read and transfer the data to the place where it's going to be reduced. Then you can run reduces. So green for map, red for reads, reduce for 1. Here's an example, again, 2,000 machines. So you can think about the complexity here. This is far less than we can do now, or far less than MapReduce is used for now. But if I asked you to take your program and have it run on 2,000 laptops or 2,000 desktops or 2,000 clusters, that is a significant problem. Instead, you just use MapReduce to write your program and call the MapReduce compiler. So here's kind of how this looks over time for a sample task. So in the beginning, we're just doing maps, right? That's green. And over time, this is going to change, right? We're going to keep changing. So here we go. And we get statistics on this. So we start doing the maps, right? And after some amount of time, the data is accumulating and is starting to shift in the read phase to the place it needs to go for the reduces. And this read phase is actually quite expensive, right? And notice the time going on here. So this starts out with 5 minutes. I'll go back. So this is at 18 seconds, we're all in the map phase. But after 5 minutes, we've started to do some reads. The reads are still going on 10 minutes later, even 15 minutes later. Finally, the maps are done, and we start to do some reduces. After 29 minutes, 30 minutes, the reduces are taking over. Finally, we're mostly reduces. The reads are finished. We're doing all the reads, and then we're finally done. So about a 38-minute task, you can see how the balancing was done for this. So about 40 minutes to do this task. So we kind of visualize what happened here and how these tasks are being completed. Now, I don't expect you to be experts at distributed computing, but I'm trying to provide some evidence that there actually is a compiler and it can take these things and distribute them if you've written your program in terms of map and reduce. And maybe I would interest you in taking a later CS class in which you looked at parallelism and distribution to see how these things actually worked. All right, let's go a little further. How are we doing on time? Oh, we have a little bit of time. I don't really want to talk too much about fault tolerance, but let me just mention that essentially if a task fails, you just re-execute it, right? Because the read is going to wait for it. So you can just re-execute these, just start up again. Now there's some other techniques as well. Seems to be pretty robust. Even if you lose a lot of these machines, you can still finish. So one experiment, they lost, nearly 3/4 to 5/8 of the machines, but you still can finish okay. So basically when a node crashes, you just can start it again on that machine or another one. Someone asked, why do nodes fail? Well, since this class started, we've had about 5 or 6 students say, hey, my computer froze, or my screen is broken, or some other terrible thing has happened. So for the same reason that your laptop might fail, machines in a cluster might fail. Lots of reasons. Heat, disk, quantum effects, bugs in the code, and so forth. Great question. All right, we don't handle failure of the head honcho yet. Now, we can also do redundant execution. So this is a strategy that you also see in universities, right? So in my laboratory, basically all the students have their own project and they help out with other projects. So there's someone in, they have going to be completing their project for their PhD or their bachelor's thesis or so forth. But there are labs at Duke and other places where they assign 5 or 6 graduate students to the same project, maybe without even telling them. And then whoever finishes it gets the paper and gets to graduate, and everyone else has to go back and work on something else. So this is very bad for the students, but it's kind of okay for science. I don't like it personally, but we can do that with machines because machines don't have feelings and machines don't have to get PhDs or bachelor's degrees, and machines don't have parents that complain and machines aren't paying us money to educate them. So what you could do is you could have lots of machines assigned to the same task, and if someone can't complete it, then one of the buddies can. You take it from the one who finishes first. So we can just have redundancy here. So again, this is a strategy that in academia I abhor because I think students and people working in labs are a protected population who are trying to get trained and do science. But in industrial settings, this happens quite a lot, even with humans. You have redundancy. And with machines, I think it's perfectly fine if you have the resources. Those are all opinions, so can't prove any of those things. So we can have extra machines there. I want to skip locality optimization, let you read about it. And I want to skip bad records on the disk. These are some of the ways. For the student who asked, why do things fail? There's some information about that, but I think I don't want to get into that here. We can do a number of other things to try to reduce failure rates, like compression, saving bandwidth, and so forth. Again, I want to refer you to these being interesting things without going into them. But let's talk about performance. How does this actually work? Like, it could be that when you distribute these tasks, it actually goes slower. So here's a little mini test by today's standard. We have some fairly small processors, and we want to do various tasks like grep and sort and so forth. We want to look at these benchmarks and look at about 1,800 machines. Again, these run now on tens of millions of machines, but let's look at a different case here, processor. So here's basically the load here, like what's happening here. So basically at peak, these guys could read, terabyte, 31 gigabytes per second. There's a lot of startup overhead for parallel programs for short jobs, but then eventually things complete and they're fairly quick. So here's kind of how this looks over time. Let's look at a sort task, which can be done in this fashion. So again, this sort task was done in about 830 something seconds here. So you have the output. So that's the load on these processors, how many are being used. So we can look at basically the bandwidth here. Now, if you do this without backup tasks, so remember on the left here, I basically have assigned one processor to one map or one read or one reduce, and they've got to finish. If they don't, there's a failure semantics. You reboot them or steal another processor, but it only happens upon failure. With backup tasks, what I do is I have redundancy. I assign several processors to each task, each map, each reduce, and so forth, right? So if I do that over here on the left, right, I'm going to complete much sooner, like nearly twice as fast. But no backup task, it takes longer. So on the right here, no backup tasks, right? One processor per task. And when they fail, you just have to restart. On the left here, I have backup tasks and they take over. You just take the one that finishes sooner. Pretty interesting. Now, one thing you can do, although it sounds a little sadistic, is you can try to make your system run slower. I can randomly go in or maliciously go in, and while this is running, I can kill hundreds of processes. Just kill them off. And when you do that, you slightly increase the running time, but not that much. So it's very robust to process failure here. And of course, this actually happens in a real setting. If you ever had a slow web page or a program crash, you can see that those things happen. So again, normal, we have backup tasks. No backup tasks, we can go slower. Even when we kill processes, it is going to be pretty fast. Okay, so backup tasks reduce job completion time a lot, and the system deals well with these failures, which is pretty neat. We don't have to write any extra code for that. It's already done for you. So what these guys did is they wrote Google's production indexing system for search using MapReduce. Unlike us, they had much longer chains, so like up to 24 nested MapReduce operations. The new code, much shorter, about 700 lines as opposed to 3,800. Automatically handles the failures. You can change new algorithms, add new machines very easily. It was quite popular. So again, the usage was, they clocked how much this was used. A lot of times, a lot of different jobs in that first year of being used at Google. And it took statistics on this, basically user studies, to see how this would work. And again, pretty interesting. How many different programs do people wrote? Well, they wrote around 200 to 400 different programs and combinations of different kinds of maps and reduces, which you can combine and recombine in different ways. And again, these ran a total of about 80,000 days to do various tasks at Google. So pretty interesting. Nice case study. So these are their conclusions. I agree with them. I didn't write these, but basically they think it's a useful abstraction. It really simplifies these large-scale computations. That means on many processors. It's entirely based on scheme functions that have this well-defined semantics. The substitution model holds. We have functional programs. And they found this is their comment. It's fun to use. You can focus on the problem. Don't have to think about all the messy details. Don't have to think about these terrible issues of parallel programming. It's going to do all that stuff for you. So basically, I want to come back to what I had before, which is we know what map and reduce are, and we've used them a little bit. We had a little example of trying to take a task, which was counting words in a document. And we tried to take that task and write it functionally and using map and reduce as much as possible. Again, you could think of map and reduce as being instructions to the compiler. They're parallel operators. They say, take this and parallelize it. And that's what the system does. So I don't expect you to be an expert in parallel programming or to know about it. I never will ask you about it. What I'd like you to get out of this lecture is that it's important to know how functional programming, map, and reduce work. And you definitely will be asked things like that. But also to take away these big points here. If you want to write parallel programs, one way of many ways to do this is use map and reduce as much as possible in the functional idiom. You will understand the serial versions that run on your laptop. And there's a claim that they will automatically be replaced by parallel implementations on a huge cluster if you want to do that. And this system handles all the details. It's like a contract. All you do is write the functional program. Again, think of MapReduce as not only as these higher order procedures that let you write these nice functional programs in this class, but operators that tell the compiler to parallelize them. And this is really in use. It's typically called MapReduce/Hadoop. It's open source. You can run it. Runs Hadoop and other places. I should also say that there are many other ways of doing parallelism, but this is one of the cleanest, and it connects very nicely with what we're doing in our class. So I think with that, I want to stop sharing, and I want to take any questions you might have on where we are and what we might like to do.
I do have a quick question.
Sure.
Are map and reduce the only parallelized functions, or are those like, is it just like the model of using map and reduce?
That's a great question. So they're not the only ones, for sure. So we definitely can have other, I mean, they're the only ones in this paper or this paradigm, but that doesn't mean you can't have other things. So other things can be parallelized for sure. But in this particular paradigm, you only need two. That's how I would phrase it. So you shouldn't think that other functions couldn't be parallelized, and you shouldn't necessarily assume that other functions could be parallelized. But in this particular way of thinking about it, they found a way really just using the functional style and map and reduce to be able to write these rather large parallel programs. So I would say it's neither, you know, in mathematical terms, it's not complete, there may be others, and it's neither necessary or sufficient for a program to have map and reduce in it to be parallelizable. But I think where I'm coming from, if the you know, previous incarnations of this class are any indication, what I would say is that generally, most people in the class haven't really thought much about how they would write a parallel program. So I'm trying to introduce it in kind of a minimalist way and saying, if you were interested, this is all you would need, and here's a thing that's widely used in industry. So I don't know if that helps, but that's kind of my position on it.
Thank you.
Sure, absolutely. Other questions? What do you think of this stuff? Is it kind of cool?
Talking about keys and values kind of reminded me of dictionary Python, even though it's pretty different in this context, but yeah.
So it reminded you of a dictionary, is that right?
Yeah, like how we thought about dictionaries in Python with keys and values.
Sure, absolutely. In fact, I would say that would be a really very similar way of phrasing it. So it's exactly the right way you're thinking about it. So I guess what I would say is, as an interface to a dictionary or a document, the keys and values are exactly the right abstraction, right? And so one way to think about that is, suppose you had some kind of operation on a dictionary, and it ran really great on your test cases, and you did problem set 3 or whatever, and you know, for your Python class, and it's like, okay, that's great. But now you're in an internship, and you have to use the same paradigm on a dictionary that's like, you know, hundreds of terabytes and distributed all over the world, and it has to be fast. So you'd have a question, which is your, first of all, is your paradigm, you know, correct for that? But how would you do it? So you go to your boss and they say, well, this is no problem at all. In fact, we have a cluster, and of course you'll need it. It has, you know, 500,000 processors. So just, it's yours. Go ahead and program it. Well, how do you program it? That's the question, right? So the setup of the algorithm is sort of fine, but how do you actually harness the power of 1,000 or 2,000 or 100,000 processors together? And so in the same way that, you know, for our Racket IDE, you know, ultimately the code that you write is getting translated through various things and into machine code and actually running on your laptop automatically, and all you see is this nice editor that helps you with syntax and errors and stuff, but that's actually happening in the compiler. So the same way that a compiler can help you write a serial program, it's nice if you had a tool like that that can help you write a parallel program, right? And so that's kind of what this provides. So when you have map and reduce, and it's doing stuff with keys and values for sure, the idea is that it's going to generate this parallel implementation for you, which is kind of a neat thing. Does that help? Make sense? Yeah, great question, great observation. Other questions?
Someone was asking about how to do 5B from the midterm and why how that relates to this lecture.
So it doesn't, it's 5B is a mathematical exercise. We're going to go over that in recitation. Although if you're impatient, we could probably do it a little bit sooner. And it only relates in that it's experience with using map and reduce in some fashion. But it doesn't directly relate to the lecture other than giving you some experience with map and reduce. Does that help? In general, I want to tell you my philosophy is that if you ask me directly, like, you know, after class, hey, how do you do this? I'll probably be somewhat Socratic about it and say, well, what do you have? And did you consider this? I'll probably help you work the problem yourself. Although with these problems, we will eventually tell you the answer if you get stuck. But I don't really believe in passive learning for these things. So we want you to kind of get unstuck with our helpful suggestions and then find the answer with our guidance. But never fear. Eventually you will be told if you're totally stuck. But my first offer, so to speak, is going to be, well, where are you? And could you try to do it now that you know that something was marked wrong? And show us that, and then we'll come back and you know, help you with it. But yeah, this will be covered in recitation for sure. Other questions?
Will you want us to like make sure we're implementing stuff like this in future like midterms? Because you mentioned at the beginning about how you wanted us to, like, a lot of our answers were super long. Do you want us to try to make those shortened in the future?
I think that I mean, again, the motivation for this would be, you know, if I took you through a super long proof where I could have shown you a smaller one, you might be saying, oh my God, why didn't you show us the short one, right? So same for code. So I'd say that you want the shortest, most elegant solution because that's what math is. And so I would say that rather than phrasing this quite as transactionally, like what do you have to do for midterm, I'd say that we want you to become mathematicians that can find a solution as short and as elegant as possible. Let me justify why that is. So I don't view proofs as being a way to actually know knowledge. They're actually a communication device. So when you're talking to someone who's mathematically sophisticated, you can convince them that a claim is true, and they can ask questions, right? So it's a way of making an argument in some sense. And you've stopped in some sense when they're actually convinced. So if you have a short, beautiful argument, they're like, oh, well, how could I argue with that? I mean, it's like, I hadn't thought of it maybe, but that's fine, but obviously it's true. Where something complex, there's lots of stuff they can pick at, they have to think about it, maybe they're too tired to think about it. So it's just, you know, advantageous to do that. So I would say that it's a goal that you'll be able to do this. And we're going to try to guide you through in the remaining parts of the class to get as close as possible. But view it as a asymptotic limit, right? We're going to try to get as close as possible to the shortest, most concise, most beautiful way of doing it. And in particular, one way we'll do that is that having tried problem 5A and 5B, we'll show you our solutions and you can, or have you work our solutions, then you can say, well, I don't think that's as elegant, or you can argue with us about it, but you can at least see what we had in mind. And also that will be a pretty big theme on problem set, at least 4, where we'll try to guide you to small solutions, even though there exist really long ones. So we'll tell you things like, hey, this took us 3 lines. You know, try to do that. That would be great. And don't use helper functions, or don't use, you know, don't use this function. And so we'll try to guide you into the shorter one so you can see how that's done for the sake of the exercise, right? So it's kind of like doing a crossword puzzle, right? If you have I don't know how many puzzles you do, but you know, if there's a word that has to fit into a slot and it's 7 letters, you may know a way to describe that in 3 sentences, right? But it's not going to fit there. So you have to find something that's short. So it's an optimization way to think about it. So we'll help you with it, and we'll be benign. And you can always ask us. Great question, though.
In one of the slides, I think Google used a for loop when they were doing the word count function. Wondering if there's any way you can do a loop in Scheme, or do you just have to simply recurse and then use kind of like car and cutter as sort of analogous to doing a loop?
That's a great question. So first of all, Scheme actually does have those constructs, but you're not allowed to use them in this class. So absolutely it's there. So basically, the analogy of, so the analogous program to a for loop is a iterative process, like tail recursion. That's typically what we would do. And so we would use that instead. So that's our form of iteration in some sense. Now, that having been said, the necessity for doing that is greatly diminished when you have high order procedures. Like you have map and reduce and so forth. We're not running for loops to accumulate those objects and traverse the list and so forth. That's done sort of automatically for you. So in a way, with these operators, even in the serial case, the need for such a thing is substantially ablated. But no, we don't use them in the class, and instead we have recursive processes, and then we have iterative processes. Those are ways of doing iteration, and you've seen that. And there's no need for the for loop. You can do it without that. And one reason is that we'd have to have a semantics for the for, right? Like when what would that even be? You have to think about it. So it would add complexity to our model.
Yeah, that definitely makes sense, especially with filter too. That kind of acts like something you can loop through.
You're absolutely right about that. Filter is exactly that same kind of thing. So filter, map, reduce, and then later with streams, we're going to see, add streams, multiply streams, all that kind of stuff. It's going to be ways of essentially iterating down a stream or a list in some sense, and without having to explicitly have a variable there to put it down the list in some fashion. It sort of does it for you automatically. So in this idiom, that's the thing that you can parallelize, and that's the thing you can reason about functionally. So great question. Any other questions?
Thank you.
Thank you. Thanks for the great discussion. I'm going to, for the class, I'm going to turn off the recording now, but I'll stay around if anyone has any questions or discussion for a while. And